तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This is the third lecture on the PN junctions and the 21st lecture of this course. In the previous lecture, we had completed the equilibrium analysis and we had obtained the concentrations of electrons and holes and then the electric field distribution in a space charge layer that is located near the junction. We also showed that the space charge layer can be assumed to be depleted of free carriers. Since Jn and Jp, that is electron and hole current densities, are 0 under equilibrium, we did not draw the distribution of Jn and Jp separately. The result of our analysis can be illustrated using this diagram. This is the depletion layer, this is the junction, and this is the electric field picture under the depletion approximation. Now, in this lecture, we will continue with the equilibrium analysis. To start with, what we will do is we will try to estimate the various parameters, namely the depletion width, the peak electric field and the built-in potential for a typical situation. So let us look at the slide which gives the details of the solved example that we are going to consider. So you have an abrupt and uniformly doped PN junction with doping levels of 10 power 16 per centimeter cube on the P side and 10 power 15 per centimeter cube on the N side. We want to estimate the depletion width, built-in potential, peak electric field, and finally we will also estimate the average diffusion current densities of electrons and holes in the depletion layer. These diffusion current densities will be very useful starting points for the non-equilibrium analysis or the analysis under bias. Now, the built-in potential psi naught, it is given by Vt ln Na Nd by Ni square. So we can calculate this as follows at room temperature. So T is equal to 300 K, that is the assumption. So we can write this as Vt into ln 10 power 16 into 10 power 15. So the power gets added here, divided by Ni square. Ni is 1.5 into 10 power 10 for silicon. So in the denominator you get 1.5 square into 10 power 20. We will shift this power up here. So that calculation becomes easy. So it is useful to keep all the powers of 10 together and all the numbers separately. This avoids mistakes in calculation. So this is equal to Vt ln 15 minus 20 minus 5 plus 16, 11. So 10 power 11 by 1.5 square. So if you take this log, you will get the result as 24.5 times Vt. So about 25 times thermal voltage. That is the kind of built-in potential you get. Now substituting Vt as 0.026 volts, you get the result as 638 millivolts or 0.638 volts. Okay, so about 0.65 volts. That is a built-in potential of a PN junction with 10 power 16 and 10 power 15 per centimeter cube doping levels. If the doping levels change, if they are more, obviously your built-in potential will be more, but note that the doping levels come in the logarithm. Therefore, the change is not so significant. So you will find that the built-in potential hovers around 0.65 to 0.75 volts for various junctions in silicon. Now the depletion width. So 2 into epsilon. The epsilon for silicon is this epsilon is epsilon silicon epsilon naught. Dielectric constant of silicon is 12 and this epsilon naught is 8.85 into 10 power minus 14 farad per centimeter. So when you multiply these two, the result is approximately equal to 10 power minus 12 farad per centimeter. So this is the number one can remember as epsilon for silicon. So since we want to collect all the powers of 10 together, we will write this power here. And also do not forget to put the units separately. Now psi naught is 0.638 volts. Then comes the Q, 1.6 into 10 power minus 19 in the denominator. This will go up and it will become plus 10 power 19. Then 1 by Nd, this should be 1 by Na plus 1 by Nd. So 1 by Na will be 10 power minus 16 and 1 by Nd will be 10 power minus 15. Now notice that we can take out 10 power minus 15 out of the bracket, so that the result will be, you will get 1 here and 0.1 here. So multiplied by 1.1. In fact, it is a common practice that when you have one side doping more than 10 times the other side, you can neglect the heavily doped side doping level. So for example here Na is 10 times Nd, so one can neglect this. The error because of that will be only 5%. Okay, one can show this. I leave it to you as a calculation. So generally it is a practice, if Na is more than 10 times Nd, then you neglect Na. The heavily doped side doping level is neglected. That is, the depletion width Xd depends on the doping on the lightly doped side predominantly. This is the important conclusion that we get from here. So let us put the units for 1 by Na and they will be centimeter cube. Let us put the unit for Q, that is coulomb. In fact, we must put the unit as and when we put the number. So here farad into volt is coulomb, this is coulomb, that cancels, and this leads to centimeter square, and if you take the square root you will get centimeter. So units are correct because Xd is depletion width. Now the result of this is, we collect these terms, 10 power minus 12 plus 19 minus 15, it results in 10 power minus 8 when you take the square root, you will get 10 power minus 4 centimeter. Then we take this number and make a calculation, and you will find this is 0.97. So the result is 0.97 micrometer, because 10 power minus 4 centimeter is 1 micrometer. This is the order of the depletion width. Now, therefore, one can remember the depletion width to be of the order of a micron for a PN junction with doping levels of 10 power 16 and 10 power 15 on the two sides. If your doping levels are higher, clearly your depletion width will be smaller. Okay? It is useful to remember values for one particular doping level, because then you can find out the values for any other doping level very quickly. Now finally the EM, the peak electric field. This is 2 times psi naught upon xd. So which is equal to 2 into 0.638 volts by xd is 0.97 into 10 power minus 4 centimeters. So if you shift this up, you will get 10 power 4. So which means tens of kilovolt. So that is why your unit will be kilovolt per centimeter for the peak electric field, and the value turns out to be 13.2. So you can remember the peak electric field to be order of 10 power 3 volt per centimeter, or sorry, 10 power 4 volt per centimeter, or tens of kilovolts per centimeter. That is the kind of electric field. So it is a very high electric field. I emphasize that this high electric field is not resulting in any current, because the current because of drift is getting balanced by current because of diffusion. Okay? So that is why there is no current for either electrons or holes under equilibrium conditions. Now finally the average diffusion and diffusion currents for holes and electrons. So let us look at this diagram, which gives you the variation in concentrations on a log scale within the depletion layer. From here one can write the average diffusion current as, for example, for holes Jp diffusion, we will put a bar here to show that these are average values. Q dp into pp0 minus pn0 by xd. So pp0 is the whole concentration on this side, pn0 is the whole concentration on the other side, and the gradient therefore can be written as pp0 minus pn0 divided by xd. Now here pn0 is much less than pp0, so you can neglect this. Further, pp0 is approximately equal to the doping level Na. We are assuming complete ionization and neglecting thermal generation. So q dp Na by xd is the average diffusion current. So you can substitute the various values. Na is 10 power 16 per centimeter cube. This is 0.97 micrometer, and this dp for 10 power 16 per centimeter cube, we have to use the mobility versus doping graph or the equation, and we will find this is approximately 35 centimeter square, 35 centimeter square per second. This is for electrons. For holes it is about 11 centimeter square per second. So you substitute everything and you will get, this is about 182 ampere per centimeter square, which is a very high current density, okay, for diffusion currents. Again, this is balanced by the drift current. We have shown that the field is very high, so you are getting a high drift current, and that is counterbalancing this diffusion current. Similarly, one can do for electrons, Nn0 minus Np0 is the difference in concentrations over the distance xd, and that will again reduce to Qdn Nd by xd, following the same approach as for holes. So this average current, if you substitute the various values. This is 10 power 15 per centimeter cube, and dN is 35 in centimeter square per second for doping level of 10 power 15 from the mobility versus doping equation. So substituting the various values, the result is about 58 ampere per centimeter square. This is the average diffusion current of electrons. Now we must emphasize that this average value should be used with caution. That is because if you see the concentrations on a linear scale, which correctly shows the variation, then you find that the electron concentration is dropping rapidly here, and the hole concentration also is dropping rapidly at the depletion edge. So our estimate, which is based on this and this line, okay. So these estimations that we have done for JP diffusion and JN diffusion, they are based on the slope of these lines and these lines. So these estimates will be way off. In fact, the diffusion current is much higher. You can see the gradient is more here in these regions, whereas in this region you will find the diffusion current values will be much less. So that is what we mean by saying that the average currents which we have calculated should be used with caution. Okay, they are only very crude estimates to get the feel for the fact that equilibrium situation in this case implies very high drift and diffusion currents exactly in balance within the depletion layer. Now let us summarize some of the quantitative values that we can carry from this example during the rest of the course. So this is shown here. Your P plus N junction, the P side is of the order of microns, whereas N side is of the order of several tens of microns. In fact, we saw it, this was 1 micron and this side was 100 micron in our real device structure. As we have said, we will be assuming that these two regions are sufficiently longer than their diffusion lengths. Now the depletion width here, that is of the order of 1 micron for 10 power 16 per centimeter cube and 10 power 15 per centimeter cube doping levels. So we remember the values for this particular doping level, then we can make calculations for other doping levels very easily. This is the electric field picture. The area under this is the built-in potential, that is of the order of 0.65 volts for the doping levels under consideration, and the peak electric field is tens of kilovolt per centimeter. This is what one must remember. Now this is a diagram which is not exactly to scale but somewhat to scale, in the sense that you can see the depletion width and the width of the P region are almost of the same order, whereas this N region width is very, very long compared to the depletion width here. This is a practical situation in a P plus N junction that you encounter. Now finally, the depletion width formula for a P plus N junction where Na is more than 10 times Nd, again this is the kind of situation we will encounter in practice, is very simple, 2 times epsilon into psi naught by Q times Nd. This formula is very easy to remember because the Q always goes with the doping, because this is the charge, ionized impurity charge, that is a space charge, okay, in the depletion layer. And then you know that the depletion width will be more if the built-in potential is more. This is very easily understood based on our knowledge of physics. We also know that the depletion width will be less if the doping is more, okay. So the doping is in the denominator and the built-in potential is in the numerator. Q always goes with the charge. Now to get the correct dimensions, you can see that the dielectric constant should appear along with the potential. This factor of 2 comes because the electric field is a triangular shape, it has a triangular shape, and the area under the electric field consists of a half term, half of depletion width into the peak electric field. So that half is coming here on this side as a 2 factor, and then you have a square root. So now let us see, if you know these values, how you can make a quick estimate for other conditions. Okay? So one example is shown here. Supposing you have a P plus N junction with the N side doping as 2.5 to 10 power 16. How do we quickly estimate the depletion width without doing detailed calculations? Now we remember that for 10 power 15 per centimeter cube it is 1 micron. Okay? And we know the depletion width is inversely proportional to the square root of doping, and depletion width will be less if the doping is more. So for this case the depletion width has to be less than 1 micron case. So therefore in the square root you put 10 power 15 in the numerator and this value in the denominator, so that you end up 1 by square root of 25, so about 0.2 micrometer. So this kind of calculation one can make by inspection. That is the advantage of remembering this approximate formula for a P plus N junction. You can always translate this formula for an N plus P junction, right? So for example, if Nd is more than 10 times Na, this Nd here will be replaced by Na. Always the depletion width depends on the lightly doped region. So that is the end of the solved example. Now so far in our analysis we have not used the energy band diagram. From the 5 basic equations we have derived the information about N, P, Jn, Jp and E. We have estimated the built-in voltage, the depletion width, the peak electric field and so on. Now we would like to look at the energy band diagram under equilibrium for a PN junction, and then we will see what advantage does the energy band diagram offer for us, what new information does it give. Now to draw the energy band diagram, what is the starting point? The starting point is a constant EF as a function of x. You would recall that in an earlier lecture when we were discussing the procedure for device analysis, we had considered the equilibrium situation, and then we had shown that if the transport equations are written in terms of the quasi-Fermi level gradients, then Jn equal to 0 and Jp equal to 0 in equilibrium translate to the gradient of the quasi-Fermi levels equal to 0, which means that the quasi-Fermi levels are constant with distance, and since the electron and hole quasi-Fermi levels are same in equilibrium, this amounts to saying that the Fermi level is constant with distance. So this is the starting point for drawing the energy band diagram. Now once this is done, the next step is to draw the energy band diagrams in the neutral P and N regions. So there, using the doping levels, we can sketch the EC and EV. So on the N side, for example, the EC will be close to EF, but since this is a neutral region and this is uniformly doped, the EC will be flat. Now you can locate the EV below this at a distance of energy gap. We can repeat a similar thing on the P side. Since the P side doping level is more than the N side doping level, EC minus EF will be more than EF minus EV. So EV will be closer to EF than EC is to EF on the N side. So this is your EV, and then we can place the EC at a distance of 1 energy gap. So this is EC. Now we need to join this end of EC to this end of EC, and we need to join this end of EV to this end of EV. While joining this, we must remember that the EC and EV, even though they may vary with distance, they must be continuous. This is because any gradient of EC represents the electric field. This point was discussed in lecture on carrier transport, that the gradient of the band edges EC and EV represent the electric field. Now you cannot have infinite electric field anywhere, so EC and EV variations cannot have any discontinuities. So you must draw continuous variations. So that is the EC and EV variations in depletion layer. We can next draw EI, that is the intrinsic level in between EC and EV. The intrinsic point is somewhere here where EI crosses EF. It lies on the lightly doped side. Now we can also draw the vacuum level E0 at a distance electron affinity from EC. So let us start from this end. So this is E0, and the same distance you should have E0 here. And now we join them by a continuous line. So that is E0, where this distance is electron affinity. This distance is Eg, energy gap. This electron affinity is in volts, so normally you multiply it by Q to indicate that it is energy, and this is energy gap. Now this EC minus EF depends on the doping level. So this EC minus EF is nothing but Q times Vt ln Nc by Nd. On the other hand, this EF minus EV is nothing but Vt ln Nv by Na, the multiplying factor of Q, because it is energy. So this is the energy band diagram of the PN junction under equilibrium. Now this has been sketched based on two principles. One is constancy of EF, and second is continuity of the band edges, that is EC, EV and E0. Now in this particular case, since we are considering a homojunction, that is this side and the other side, P and N side, both are made of the same material, E0, EC and EV, all three were discontinuous, and in fact E0 was not necessary while drawing the energy band diagram of EC, EV and EF. So E0 was drawn at the end. However, in the case of heterojunctions, the picture is somewhat different, because when the materials are different on the P and N side, your energy gaps are not the same on P and N side, and therefore if you look at this diagram, if this energy gap is not the same as this energy gap, then obviously somewhere there will be a discontinuity either in EC or in EV or both. Now that being the case, it is important to note that in such situations it is the E0 which should be maintained continuous, because E0 represents the energy corresponding to an electron which is just outside the crystal. So electron here, this is the PN junction. Now if you move the electron along this junction, touching this junction from outside, it is obvious that this electron should not encounter any infinite electric field here. That will be non-physical. Since the gradient of E naught represents the electric field at this location here, therefore this the E naught should be a continuous line, because any discontinuity in E naught would mean an infinite electric field for this electron wherever the E naught is discontinuous, and that is not possible. That is why one states the two conditions for drawing energy band diagrams in general under equilibrium conditions, and they are that EF should be constant and E naught should be continuous. The fact that EC and EV are continuous in a homojunction follows directly from the continuity of E naught, because EC should be drawn electron affinity below the E naught. So this is EC is parallel to E naught, and since E naught is continuous and electron affinity is the same throughout, therefore EC, which is parallel to E naught, should also be continuous, and EV, which is parallel to EC, should also be continuous, because energy gaps are also same. So we can summarize this by writing the two principles are constancy of EF and continuity of E naught. So these are the principles for drawing energy band diagram. Now we will do an example to give you a feel for the values of some of the parameters on the energy band diagram, and also how an energy band diagram can be drawn for a given condition. An abrupt silicon PN junction is doped uniformly with 10 power 16 per centimeter cube atoms of boron on the p side and 10 power 15 per centimeter cube atoms of phosphorus on the n side. Draw an energy band diagram of the junction to scale by a systematic approach. Assume room temperature. Note that the phrase to scale has been underlined. So various parameters should be drawn to scale to get a correct picture. Now let us proceed. The first step in the drawing of energy band diagram is a constant EF. So draw a constant EF. The second step is to locate the junction. So here you can see the junction has been located on this constant EF line, and then after locating the junction we should locate the depletion edges. So in this case it is the depletion edge on the p side, which is located at a distance of xn, xp. So before drawing the energy band diagram, the calculations of depletion width, built-in potential and so on should be completed. So xp on this side and xn on the other side. So this is xn. So locate the junction xn and xp. So xn and xp represent the depletion edges basically. Now after doing that, you draw the diagram in the neutral regions, p plus and n regions. So third step is draw EC, EV, EI and E naught in neutral region. So to do that, we must know on the n side where is EC. This can be done as follows. You use the formula EC minus EF on the n side is equal to KT ln NC upon ND. We are assuming complete ionization and neglecting thermal generation. So the majority carrier concentration is equal to the doping. Now you substitute the values. For silicon, this is 10 power 19 into 2.8 per centimeter cube, and this is 10 power 15 per centimeter cube, and KT at room temperature is 0.026 electron volts. So the result is you will get this as 0.27 electron volts. So we locate EC here. This is EC. And this difference is 0.27 electron volts is the difference. Now if this is 0.27, we must locate the EV at one energy gap below. So energy gap is 1.1, that is almost 4 times this. So since we want to draw it to scale, we must choose 4 times this, and somewhere here is your EV, and EI is about halfway, so that is here. This is EI. Now we should complete a similar exercise on this side, on the P side. So for P side, you have EF minus EV is equal to KT ln NV upon NA. Then you substitute value of NV, which is 10 power 19 per centimeter cube in silicon, and Na is 10 power 16 per centimeter cube. And so the result is, at room temperature, this is 0.18 electron volts. So since we want to draw it to scale, notice that 0.18 is 2/3 of 0.27. So 2/3 of this distance, you must locate the EV here. So this is EV. And now we should locate the EI and EC. So EI, this is half of energy gap, so about that distance, and then this is EC. So this difference is 0.18 electron volts, and this difference is 1.1 electron volts energy gap. Now we should also locate E naught. So E naught minus EC is electron affinity. Now the electron affinity chi into Q, this is 4.05 electron volts for silicon. So this distance is 1.1 and 4.05 would be a little less than 4 times this distance. So we must locate 4 times this distance here. So less than 4 times. So somewhere here is your E naught. This is E naught, and this difference is 4.05 electron volts. We do the same thing here. So this is 1, this is 2, and this is about 2.5. So 1, then 2, and 2.5. So that is somewhere here. That is E naught. So this side also, this difference is 4.05 electron volts. Now the next step is to complete the band diagram in the depletion layer. So fourth step, draw E naught as a continuous line within the depletion layer. So that you can do something like this. So this is what is done. Now what is the shape of this line? Now notice that this line indicates the potential within the device. We have already sketched the potential as a function of x. So since the electric field is linear, the potential is parabolic. So you have one parabola here and another parabola here. They are the two parabolas. So this follows exactly the shape of the potential, except that the potential which you plot is for a positive charge, whereas this energy band diagram is for negative charge. That is the difference. So having drawn E naught, now you can draw EC, EV and EI all as parallel to E naught. So within the depletion layer, sketch EC, EV, EI and impurity levels. Parallel to E naught. So let us do that exercise. So parallel to E naught, we sketch EC, then we sketch EV, and we sketch EI. And then also the impurity levels. Now where will the impurity levels be? On the N side, the donor level is close to EC but at a distance of 0.05 electron volts. Now if you compare 0.05 electron volts, which is the ionization energy of phosphorus, with 0.27, 0.27 is a little more than 5 times 0.05. So which means that 1/5 of this distance between EC and EF is the impurity level. So approximately we are locating it here. So this is the donor level. So in the entire region the donor level is very close to the conduction band edge. So this is ED. Similarly one can draw EI on this side. So EI is also at 0.05 electron volts from the valence band edge, not EI, EA. So this is EA, the acceptor level. Now notice that acceptor level has to be drawn parallel to EV here. So the donor level is also going to bend like the conduction band edge and other levels like EI and EV. So with this the energy band diagram is complete. So this is how an energy band diagram will look like when drawn to scale for a silicon PN junction. Now let us look at some of the advantages of this diagram. What information does it give that we have not obtained from our analysis based on the 5 basic equations, wherein we drew n, p, jn, jp and e as a function of x. Now first thing here, the built-in potential is the difference between the EC on the two side, or it could be EV on the two side or EI on the two side, or it could also be E naught. So this difference is the built-in potential. So this is 0.638 volts. We have already calculated this value. What about this distance xn and xp? This xn is xn plus xp, this total distance is 0.97 microns. We have already calculated this. Now if you take into account the fact that doping is 10 times on the p side as compared to n side, you will end up getting a value of xn 0.88 micrometer and you will get xp to be 0.09 micrometer. So coming back to our discussion on what advantage does the energy band diagram offer. Notice the donor level here, okay, it is varying with distance. So this means that the extent of ionization is changing with distance within the depletion layer, because the difference between ED and EF is what shows the extent of ionization. You know that ND plus by ND is equal to 1 minus 1 by 1 plus exponential of ED minus EF upon KT. Of course here you have to multiply it by degeneracy factor, but we are ignoring in our course this degeneracy factor as we have told right in the beginning. So this is the equation that we had written down in one of our earlier lectures for ionized impurity concentration. Similarly one can write the expression for Na minus by Na, and this is nothing but 1 by 1 plus exponential of Ea minus Ef upon Kt. So the difference Ed minus Ef decides the extent of ionization, and difference Ea minus Ef decides the extent of ionization for boron here. So since Ed minus Ef is changing, you can see this with distance, it means the extent of ionization is changing. Now since in our problem the extent of ionization is almost complete, this is not really giving any significant information because already the extent of ionization is complete. So if it changes little bit, it does not make any difference. But you will note that if the doping level is heavy and if this Fermi level moves close to the donor layer or the donor level, then the extent of ionization change that is shown by this difference EF and ED will be significant, and your space charge picture will be therefore affected. In other words, in the space charge region, your space charge concentration will not be exactly Q times Nd, it will be Q times Nd plus. Let me show this with an example. Suppose apart from the shallow donor level which is present there, there was a deep level. Let us say that is also a donor type. The donor level, the deep donor level, say is at EI, that is the intrinsic level itself. What would happen? Look at the diagram. So if you had a donor level along EI, then you can see that in this portion of the depletion layer, the donor level, the deep donor level is below EF. On the other hand, in the remaining portion of the depletion layer on the N side, this donor level would be above EF. Since the levels below EF are all occupied, a donor level below EF means an occupied donor level, which means an unionized donor impurity. So in this region you will have partial ionization. In fact, ionization will be very poor, and gradually the ionization will improve as you move and will become very good near the junction. So from partial ionization to complete ionization, the state of ionization of the impurity is changing within the depletion layer. Therefore your space charge picture also will be affected. Let us draw the space charge picture for an impurity that is crossing the Fermi level. So we are assuming a donor impurity which crosses the Fermi level, the picture being as shown in the band diagram here. So a portion of the band diagram which shows EF crossing ED is shown here. This is the depletion region. So this is Xn, the portion of the depletion layer on the N side. If you draw the space charge picture, it would be something like this. So this is Q times Nd plus, not just Nd but Nd plus. This is the ionized impurity concentration. So information such as this is revealed by the energy band diagram, something that we cannot obtain without the help of the energy band diagram. Now let us summarize how the information given by the 5 basic equations is reflected in the energy band diagram. So let us look at this picture. The fact that Jn equal to 0 and Jp equal to 0, that is information from the transport equations, is reflected in the fact that the Fermi level is constant. So this is the Fermi level, it is constant with x. So EF constant with x, this is the information from the transport equation. Next, the fact that there are no excess carriers, that is the same EF is applicable for both electrons and holes. So EFP equal to EFN. Or delta N equal to delta P equal to 0. So this is information from the continuity equation. So the effect of the continuity equation is again shown in the same Fermi level which is drawn here, from the fact that the same Fermi level is being used for electrons as well as for holes. So this is from continuity equation. Now, what does the Gauss law say, or what does how the information from the Gauss law is reflected in this energy band diagram. This is reflected in the shape of the EC, EV and the other levels in the energy gap. So, shape of EC, EV, ED, EA and EI variations. So this is obtained from Gauss law. So for example, this region the EC is flat, this means there is no electric field here, okay, and also there are no space charges, whereas here the shape will be parabolic. So this parabolic shape is again obtained from Gauss law. This region XD, and these are electronic energies. So within this region the shape is parabolic. This is again obtained from the Gauss's law. So this is how the information from the 5 basic equations is clearly reflected in the energy band diagram. So there is a one-to-one correspondence between various aspects of the energy band diagram and the 5 basic equations. So with this we come to the end of this lecture, wherein we considered the equilibrium analysis. Quantitatively we solved an example to show the typical values of depletion width, built-in voltage and the peak electric field, and then we also saw how we can draw an energy band diagram under equilibrium conditions.